recap the stop and wait. We send our data. We stop, the source stops and waits for an ACK to come back, and then it's allowed to send another data frame. And we just continue doing that while we have data to send. If we don't have data to send, we don't send anything. Simple. But we may be allowed to transmit. So it's about when is the source allowed to transmit the data frame. The idea is that the receiver has enough buffer space to receive one data frame. So what happens is that the receiver receives one data frame, stores it in the buffer, does some processing. When it's processed and removed from the buffer, the receiver sends back an ACK saying, please send me the next one. I'm ready for the next one. So one at a time in this case. So since the receiver has buffer space for one data frame, with stop and wait, the source will never send two data frames or never have two sent without an ACK being sent saying we're ready for the next one. So we'll not overflow the buffer. Very simple. And we got a throughput in our example of 959,000 bits per second. And the other way we can look at the performance is the efficiency. The throughput is the rate at which the real data is delivered to the destination. We talk about the real data, this payload of 1,000 bytes per frame. In fact, we had three data frames. We had 3,000 bytes, but it turned out in our case it just keeps repeating. Send 1,000 bytes every 8,341 microseconds, and then send another 1,000, and then another. If you had 3 million frames, it would just keep repeating. So we, on average, we're sending 1,000 bytes of payload every 8,341 microseconds. Gives us our throughput. The efficiency, we can say, is the rate, the efficiency is the percentage of time that we use our link to deliver real data. Throughput is the rate at which real data is delivered. Efficiency is the fraction of time or the fraction of the link that we use to deliver real data. The complex way to calculate it, think of our stop and wait. It looks like this. The total time was, we calculated as 8341. During this 8,341 microseconds, how much time are we transmitting real data? When are we transmitting real data? Well, this is when we're transmitting data, the data frame. Let's say this is the real data, because in the data frame, there's a small part which is the header. That's not the real data. So in terms of this total time, some time is spent transmitting the header, some time is spent transmitting the real data, and some time is spent waiting. The question is, how much time do we spend transmitting the real data related to the total time? Well, how big was the real data? 1,000 bytes. How much time transmitting 1,000 bytes? It depends upon our data rate, 1 megabit per second, which is 8,000 microseconds. The transmission time for the real data is 8,000 microseconds. Of the data frame, we had a transmission time of 8,160. It's 8,000 of real data, 160 of header in our case. So our efficiency, transmit real data for 8,000 microseconds. Total time is 8341. And that gives us a fraction. We can also express that as a percentage. What's the value? 8,000 divided by 8341. .9591118. Or I'll write that as a percentage, 95.9%. 95.9% of the time, we're sending the real data. The other 4.1% of the time, we're either transmitting the header or waiting for some ACK. That is, although my pitch is not very good because it's not to scale, this represents 95.9% of the total time in our case. That's our efficiency. The simple way to calculate that is simply the throughput divided by the data rate. 959,118 divided by 1 million divided by our data rate. That gives us the efficiency. You can do the mathematics and see that they're the same. This was 1,000 bytes divided by 8341. This is 1,000 bytes divided by the data rate divided by 8341, which is really just this divided by the data rate. Efficiency is the fraction of time that we spend transmitting the real data or receiving the real data. Now, let's change a parameter. With our question, we had a 2-kilometre link, and that gave us a propagation delay of 10 microseconds yesterday. Propagation of 10 microseconds. Let's increase our link. Everything else is the same, but let's say the link is 200 kilometres. It's 100 times larger. What's the propagation delay? If the link is 100 times larger than in the original question, the propagation delay will be times 100, which is 10 times 100. 1,000. Okay. Propagation delay, let's do the same calculation as before, as yesterday, but use a propagation delay of 1,000 microseconds. We'll do it quickly. First, I'll try and draw what it would look like. Yesterday's, and I'm only drawing for one frame. Yesterday we went through 3 frames, but it turns out they were the same. Yesterday, if we draw it closer to scale, it would look something like this. Well, I've changed the scale here, but we transmit the data, propagate, process, a little bit of processing here, ACK, propagate back. That's the general form. Turns out for yesterday that the time spent transmitting data is 95.9% of the total time. That is, the time here is, and again it's not quite to scale, but of the total time, the time spent transmitting data is about 95.9% of it. That's our efficiency. Same values, but let's increase the propagation delay. So the transmission time will be the same. So if I try to draw it about the same transmission time. Propagation delay was 10 in the original calculation. Now it's 1,000, so it's much bigger. So maybe I'll draw it like this. And then there's a small processing and a small ACK, and then a large propagation delay. Total time from the start, 0 to the end, the time when we receive the ACK. We're spending some time sending the header and not 95.9% anymore, but some time transmitting the data. Which one is going to be higher efficiency? The original one, yesterday's, or this new one with a longer propagation delay? Which one's higher efficiency? Yesterday or today? Yesterday. Yesterday's calculation, we see from the diagram we spend more time sending data. With an increased propagation delay, we spend more time waiting for an ACK. That's inefficient. So yesterday, this is the time spent sending data out of the total time. With this new calculation, same amount of time transmitting the real data, but much more time waiting for an ACK to come back. Much less efficient. Increasing the propagation delay reduces the efficiency of stop and wait. That's the thing you can take from here. Because we have to wait longer for an ACK before we can send the next frame. What is the value? This will be the same as before. It will be, what is it, 8160 plus 1000 for propagation, not 10. We had a processing of 1, an ACK of 160 plus another 1000. If we start at 0, it brings us to, if we add all of them up, 10,321. Yesterday, if we started at 0, we finished at 8,341. Increasing the propagation delay increases the total time, and our efficiency is now our 8,000. We still spend 8,000 of this 8,160 transmitting real data out of the total time of 10,321. I had the answer somewhere. About 77.5%. Increasing the propagation delay decreases our efficiency of our stop and wait protocol. What else decreases the efficiency of stop and wait? How else can the efficiency go down? What else could change that cause the efficiency to go down? You can look at the equations, you can look at the picture and try and work out what causes the total time to go up or the fraction of the transmit time compared to the total time to go down. Data size. What about the data size? How will the data size, or what will reduce the efficiency? More data, less efficient. Try and draw it. Rather than calculating, let's compare the first one to the second for a new one. Less delay of what? Well, let's go back to the first one where we have a small propagation delay. Let's increase the data size. So I would draw it like this. The data is much bigger, and then we have our small propagation, small ACK and processing. As a fraction of the total time, this one compared to the first one, which one's more efficient? This new one's more efficient because as a fraction of the total time, we spend more time transmitting the data. It's only a small, very small amount of time for header, and relative to all of this, only a small amount of time for propagation. So this would be more efficient than this. Because as a fraction of the total time, in the first case, the time spent transmitting the real data is less than in the new one. Increasing the data size, the payload, with everything else fixed, increases our efficiency. And you can see what other factors. Well, the transmission delay depends upon two things, the data size and the data rate. Increasing the data size increases the efficiency. Decreasing the data rate increases the efficiency, because really it's increasing the transmission time, and the real data transmission time increases the efficiency. So if you make, what do we have, the transmission, if the header is fixed, if this goes up, the efficiency will go up. That is, if we send more data or we send at a slower rate, the efficiency will go up. To check those things, and we're not going to do it now, but in the email I sent, and you can download it from the website. Now first, you should be able to calculate, draw the diagrams and calculate for some scenario. But to check quickly, assuming the fixed size header, how do you increase the transmission delay? You increase the data size, like here, or you reduce the data rate, which is also lead to this case. Transmission time of the data depends upon the header, the payload, and the data rate. Assuming the header is fixed, small, increasing the payload will make the transmission time go up, and we'll get something like this. Or decreasing the data rate will make the transmission time go up, which will also look like this if we draw it. And this is more efficient than our previous one. But sometimes that's hard to think about, and this spreadsheet will calculate and show you. Increasing the propagation delay is this one. Assuming everything else is fixed, going from our original one, propagation of 10, to propagation of 1000, reduces the efficiency, because we spend less time of the total transmitting our data. Increasing propagation delay reduces, increasing transmission delay increases in general. Go back, then we'll come. In general, for stop and wait, when the data transmission time is much larger than the propagation time, we'll be efficient. So in general, although there's processing and header and so on, but in general, the main contributors are the data transmission and propagation. If we have a high transmission time compared to propagation, like here, high transmission compared to propagation, efficient. And here, the propagation is a large contributor. The propagation takes up most of the time compared to transmission, so less efficient here. And the opposite, inefficient, when you have a low transmission time or a high data rate. If you send very fast, the propagation will be large compared to the transmission, data transmission. Large distance, of course, large propagation. That's bad. Or small frames as well, a large amount of header. So there are some examples when it becomes inefficient. You can use this, try this spreadsheet, you can download, and it's very simple. All it does is calculates those values of throughput and efficiency for you. So you just plug into the boxes the values you want, and it updates the calculated values. For example, this was the one from yesterday. Throughput was 90, or efficiency was 95.9. If we change our length to not 2 kilometres but 200, and in fact I've got the length in both directions, they should be the same, it doesn't update. Why? I think I've got the the wrong one. Why doesn't it update? Something's wrong. Well, I need to check that. I don't know if that's the right one that I've uploaded, but changing the length of the distance, see we calculate 10,321, which is what we calculated here. But my calculation of efficiency is wrong. Original length of 2 kilometres brings us down to the 8341. Unfortunately, I've converted this from Excel to OpenOffice. Maybe that's caused my problem. I'll check that. But you can use the spreadsheet and plug in these values. It gives you the total time for you, and if I get the right one, it will give you the throughput and the efficiency as well. But still, you should be able to calculate them yourself. But this is just to change some values and see the impact of those values. Let me get back to you on that one. So, that's stop and wait. It can be inefficient when we have a high data rate, long links. We want an alternative. In those cases, we need something different because it can be very inefficient in some cases. The problem with stop and wait is this. We spend a lot of time waiting for the act to come back, and we waste that time. We should be transmitting some data. But if we have a long propagation delay, we don't transmit anything, and that leads to the inefficiencies. The alternative to the stop and wait is called sliding window flow control, and it's more complex, but the concept is with sliding window is to allow the source to transmit multiple frames. With stop and wait, we can transmit one and then wait for an ACK. With sliding window, the idea is to allow them to transmit 1, 2, 3, and then wait for an ACK. Depending upon the scenario, if we allow to transmit more frames and then wait for an ACK, then we spend more time transmitting, less time waiting. Now we just spend a small amount of time waiting. That's the concept of sliding window. Allow the source to send multiple frames before having to wait for an ACK. Even with a large propagation delay, we can cut down the time spent waiting and therefore increase the efficiency. In fact, we can reduce it to 0 in some cases. So let's explain how sliding window works. We'll come back to the size of frames. Stop and wait allows the source to send one frame and then it has to wait for an ACK. We can say that that one frame is in transit or it's outstanding. From the source's perspective, I send it, it's somewhere on the link and the ACK is somewhere coming back. I have to wait until the ACK comes back. So we can say that we can have one frame on the link at a time or one frame outstanding before I have to wait for an ACK. With sliding window, we want to allow the source to send multiple frames before having to wait for an ACK. We can have multiple frames outstanding before waiting for an ACK in transit. We'll look at how we can do that. If we allow the source to send multiple frames, we're going to need to keep track of the frames, because there's going to be multiple acknowledgements coming back. We will give the frames numbers. Okay? So we'll now introduce sequence numbers, where each frame that we send, inside the header, we include a number to indicate this frame in the sequence of data that we're sending. I have 1,000,000 bytes to send. I break it into 1,000 bytes per frame. Then the first frame will give sequence number 0. We'll start at 0. Then sequence number 1, 2, 3, and so on. We'll order those frames with sequence numbers. We'll include the sequence number in the header, but because the header size is limited, the number of bits we have to store the sequence number in the header is also limited. We cannot store an infinite number of, we cannot count up to an infinite number of sequence numbers. We have a fixed number. So if we have a k-bit sequence number, what we do, first frame is 0, 1, 2, 3, up to 2 to the k minus 1, and then we wrap back to 0. 0, 1, 2, 3, and so on. Let's illustrate that. Let's say my source has 1 million bytes to send. And we break them into, well, each frame contains 1,000 bytes of data, of payload. So the first frame contains 1,000 bytes of data. If we use a 2-bit sequence number, with a 2-bit sequence number, we store in the header 2 bits. So in decimal, we can represent the values 0 through to 3 with a 2-bit sequence number. So what we do is the first frame gets a sequence number 0. The second frame also, which contains the next 1,000 bytes of data, sequence number 1. The third frame 2. The fourth frame 3, and the fifth frame, what is it?
0.
Now we need to wrap around, because we can only store the values 0 through to 3. We only have 2 bits available in this case. So the sixth frame will be 1. So 0, 1, 2, 3, 0, 1, 2, 3, and so on. So of those 1,000 frames, we just order them and use the values 0, 1, 2, and 3. With a 3-bit sequence number, as an alternative, we can store 0 to 7. So it would be 0, 1, 2, 3, up to 7, and then 0, 1, 2, and so on. Okay, that's how we use our sequence numbers. They are used to keep track of the order of the data out of the total, and used for, in sliding window, used for the source and receiver to keep track of the frames which have been sent and acknowledged. So that's sequence numbers. How does sliding window work? What we want is to allow the sender to send a window of frames. Stop and wait, the sender can send 1 frame and then wait for an ACK. Sliding window, we want to allow them to send, let's say, W frames and then wait for an ACK. To do that, we keep track of the frames sent and received. Let's explain how that happens. Let's say, I don't know if you, all right, let's draw stop and wait first. Maybe stop and wait looks like this. Here's the data frame. There's an ACK here, but because it's small, I will not draw it. But propagate, there's a small ACK here, and then propagate. Let's make it more interesting. Let's make the propagation delay much larger, very inefficient. And so on. Stop and wait, transmit a data frame, wait for the ACK to come back, and so on. With sliding window, let's say instead of allowing to send 1 frame, we allow them to send 7 frames. So we send 1, 2, 3, we send 7 frames. with sliding window, and we'll give them sequence number 0, 1, 2, 3, 4, 5, 6. And the same, we transmit them, we wait for the ACK. After sending 7 frames, in this example, we must wait for the ACK. And once we receive an ACK, we can send more frames. Sequence number, the next one after 6 will be 7, and then we'd wrap around to 0, 1, and so on. So the idea with sliding window is to allow the source to send multiple frames before waiting for the ACK. In this example, 7. We'd say the maximum window size, or W in this example, is 7. The maximum number of frames the source is allowed to send before waiting for an ACK, in this example here, is 7. What the source does is keeps track of those frames which it has sent and which have been acknowledged, so that it knows how many it's allowed to send. Because if the maximum is 7, I'm allowed to send. If I have sent 3 already, then I'm allowed to send another 4. If the maximum is 7 and I've already sent 6 frames, I'm allowed to send 1 more. If I've sent 7 and not yet received an ACK, I must wait for an ACK. That's the idea. I'm allowed to send a maximum of 7. If I've already transmitted 7, like in this case, I've transmitted 7. Now I've transmitted the maximum. I must wait until I receive an ACK. And receiving an ACK allows me to send 1 more frame. I transmit that frame. I'm not allowed to send any more, but hopefully I'll receive another ACK shortly later, allowing me to send another one. The idea, we have a maximum we're allowed to send. As we receive ACKs, we're allowed to send more. As we transmit, we're allowed to send less. So the sender keeps track of this, how many it's allowed to send and how many it's already sent, by recording, let's say, 3 variables. The last frame acknowledged, the last frame transmitted, or the sequence number of the last frame acknowledged, the sequence number of the last frame transmitted, and the current window size. We'll use this example to illustrate these variables. And then we'll use the one in front of you to illustrate it, the coloured one. So 3 variables. What this diagram shows is a sequence of frames and their corresponding numbers. So I'm drawing a frame. Okay, the first frame I transmit is some square, and then the second, the third, and so on. And of course we give them sequence numbers, and they may wrap around those sequence numbers. So that's what this diagram represents. Each square is a frame and its sequence number. There may be more back here. So in the past there were some frames, and in the future there are many more. Maybe we have 1,000 to send. This is just a selection of the frames, in this case 16 frames. And the sequence numbers of those 16 frames in this example go from 0 to 7 and then 0 to 7. Because in this example we're using a 3-bit sequence number. So we've got a 3-bit sequence number. In the example we have a maximum window size of 7. The sender records 3 variables, 3 values that change over time. At some point in time, some frames have already been transmitted and also acknowledged. And in this diagram it says that frame number 5 is the last frame acknowledged. What that means is that the sender has already sent frame 0, 1, 2, 3, 4, 5, and it's received ACKs for 0, 1, 2, 3, 4, 5. So the last frame in the sequence that was transmitted, it's already transmitted and acknowledged, is 5. in this example, at this point in time, also the source has sent frames 6 and 7. So my computer has sent many frames. It's received ACKs for all of these. It's also transmitted frames 6 and 7, but it hasn't yet received an ACK. We'll illustrate that where? Not with this one. And there's more before 5. 5, 6 and 7 have been transmitted, and we've received an ACK. Let's say somewhere we received an ACK for 5. So at this point in time, 5 has been transmitted and acknowledged. That's shown here. 5 has been transmitted and acknowledged. 6 has been transmitted, 7 has been transmitted, but at this point in time, we haven't yet received an ACK. We should receive one in the future. Maybe we're going to receive it later here. But at this point in time, the current value of the variables would be the last frame acknowledged is 5, the last frame transmitted was 7, and it hasn't yet been acknowledged. So 6 and 7 have been transmitted but not acknowledged. Everything before transmitted and acknowledged. My maximum window size is 7. That's the maximum number of frames I can have outstanding. I've transmitted 2 and I haven't yet received an acknowledgement, so I'm allowed to send another 5. That's the idea here. The maximum number of frames I'm allowed to send without receiving an ACK is 7. I've sent 2, so the current window size is 5, and that's shown by the blue rectangle here. 6 and 7 have been transmitted, not yet ACKed. 0 through to 4, that is, there is 5 frames, are allowed to be transmitted. We call that our current window. So the variable values, the last frame ACKed, in this example is 5. The last frame transmitted is 7, and the current window size is 5. These two values are sequence numbers. This value is the number of frames, so they're counting different things. 5 is this value, 7 is the last frame transmitted. Current window size is the length of the blue rectangle. It's 5 frames. Or alternatively, we could store the value 4. It would also work. So the source keeps track of these values so that they know what acknowledgements they expect to receive and what they're allowed to send. If sometime later we receive the ACK for 6, so here, what is the value of this? Last frame ACKed. Sometime later I've received the ACK for 6, so these 3 variables are going to change. What's the value of the last frame ACKed? 6, okay? Before it was 5, but now I just receive an ACK for 6, so the last frame ACKed becomes 6. That changes to 6. What about the last frame transmitted? What's the value? Last frame transmitted. Last frame ACKed means the last frame transmitted and acknowledged. Last frame transmitted means last frame transmitted but not yet acknowledged. So it's still 7. In this case, I haven't drawn any more frames. It's still 7. And the current window size? Six. Why? Maximum window size is 7. I can have 7 outstanding. I've transmitted 5, 6 and 7. I've received ACKs for up until 6. So there is 1 frame outstanding, frame number 7. Currently 1 frame outstanding. I'm allowed to have 7 outstanding, so I'm allowed to send another 6. Okay, the current window size is 6. Graphically, what you would see here is that this vertical bar, when I receive an ACK for 6, it moves to here. 6 moves into the set which have been transmitted and ACKed, and the blue rectangle moves 1 position here because 7 is outstanding plus another 6 could be outstanding, because between the vertical bar and the right of the blue rectangle is always 7 in this example. The blue rectangle is our window, or the concept is it's a window. And as we receive ACKs, we're allowed to send more data. When we receive an ACK for 7, we can send 1 more. As we transmit more frames, then we're allowed to send less, such that the maximum outstanding is always 7. Between here and here is always 7 in our example. The receiver does something similar. It keeps track of the frames which it has received and sent an ACK for, the frames which it has received and not yet sent an ACK for, and its current window size. It's very similar at the receiver. Let's explain that with a different example. And the example is the one you have in front of you, the coloured one. Who doesn't have one? This is just the coloured version of the last. It's in your handouts, the black and white version, but it looks better in colour. Anyone else? 10 baht for you. No? Not really. Okay. It shows an example, and in this case I've got some numbers, but ignore the numbers for now. We'll come back to them and do some calculations with them. Let's try and show what happens. In this case we have a 2-bit sequence number. Okay, so our sequence numbers are 0, 1, 2, 3, 0, 1, 2, 3, and that's shown here. This is the data that we have to send from source A. Has a lot of data to send. Each data frame will get a sequence number in order. With a 2-bit sequence number, the maximum window size, W, is 3. We'll explain later what the relationship between the sequence number and the maximum window size. What happens? What we'll draw here is the information that the source keeps track of. I will not write the values of these, but we'll see it graphically. The idea is that the green squares are frames which have been transmitted. Sorry, the green ones are frames which we're allowed to transmit, not yet transmitted. So we're allowed to send them because the window says we're allowed to send some number of frames. 3 is the maximum. Red are those frames which have been sent. So A has sent the frames, but it's still waiting for an ACK. And the grey ones later we'll see are frames which have been sent and we've received an ACK. We say that those frames have been successful, they're complete. I've sent the data, I've received the ACK, let's move on to the future frames. So that's the colour coding here. Initially, at time 0, we've sent nothing. Maximum window size is 3. So we're allowed to send 3 frames. Frames number 0, 1 and 2. So that's what we're allowed to send at the start. We can only transmit 1 frame at a time. So we transmit the first frame, frame 0. So after starting the transmission of frame 0, that becomes a frame that is transmitted but not yet ACKed. Okay, so that's why the 0 becomes a red one. We've transmitted it, but we're still waiting for an acknowledgement for it. So at this point, the last frame act, there'll be no frame act at this point. Last frame transmitted would be 0. Current window size would be in this one. What's the current window size? Maximum is 3, the current is... Current window size means the number of frames I'm allowed to send. How many am I allowed to send at this point?
2.
I've sent the red one, I'm allowed to send 2 more. You'll see that the red plus the green squares should always be 3. It should always be 3 squares. So I've sent 1, I'm allowed to send 2 more. So I transmit the next one. Okay, I transmit frame 1. And then that changes. 0 and 1 are transmitted or outstanding. I'm allowed to send 1 more. So let's transmit the next one. And now 0, 1 and 2 have been transmitted. I'm not allowed to send any more because the maximum I'm allowed to send without getting an ACK is 3. And there's no ACKs yet. Let's follow the diagram and see when we receive an acknowledgement. It takes some time for the ACK for the first frame to come back. I transmitted at time 0. There's a transmission time of 100. There's some propagation time, and then the ACK is transmitted back, and eventually I receive the first ACK. The acknowledgements also contain sequence numbers to tell the source which frame they're acknowledging. We've sent frame 0, this acknowledgement comes back. What do you think the sequence number is in that acknowledgement? What do you think the sequence number is in the acknowledgement? Anyone want to have a guess? Feel free to yell it out anytime. Let's say this is our first data frame. It has a header and some data or a payload, the actual real data. Inside the header are different values, including probably the source address, the destination address, and the sequence number. In decimal, 00, in binary, because we've got a 2-bit value in our example, in binary here, 00. That's our first frame. An ACK comes back, so that's our data frame. We transmit that, and an ACK comes back. An acknowledgement, draw it a bit better, is normally just the header. There doesn't have to be data included. So the ACK, and inside the header there's also a number. We will call it normally an ACK number. So in our example, I've transmitted frame 0, it's arrived at computer B. Computer B sends back an acknowledgement, and inside that acknowledgement it includes an ACK number, or the number for the acknowledgement. What value should it include? I'm acknowledging the reception of the first frame, frame number 0. What number in the ACK? The ACK field. Have a guess. 0. All right, that makes sense. I send frame 0, sequence number 0. When someone acknowledges it, they send an ACK with sequence number or number 0 in it as well. Okay, saying thank you for frame number 0. I'm acknowledging frame number 0. And when I send frame number 1, and then B sends back an acknowledgement, sends an ACK number 1, saying thank you for frame number 1, here's an acknowledgement. Unfortunately, it doesn't work like that. It can, But in practice, what happens is the ACK number in almost all protocols, it indicates what's the next number it expects. So I send data frame 0, B receives it and says, thank you for that. I now expect frame number 1. So that's what's used in practice. And later when we look at error control, we'll see how the benefits of that become useful. It's even useful in sliding window. So just remember, if I send data with sequence number 0, the ACK comes back with an ACK number saying the next value expected. The next value is 1. So send data 0, come back with an ACK, thank you, I now expect data 1. Send data 1, thank you, I now expect data 2, and so on. That's how ACK numbers are used. Back to our sliding window. Here's the ACK coming back with acknowledgement number 1, acknowledging the first frame. Comes back, and when we receive that ACK, before we were not allowed to send any frames. We receive the ACK, and from it we understand that frame number 0 has been acknowledged. If it says the next I expect is 1, then we can assume that everything before 1 has been ACKed. So frame 0 has been successful now. 0 has been transmitted and ACKed. We've got 2 outstanding. We're allowed to send 1 more because the maximum allowed is 3, the red plus the green. Receive the ACK and our window opens up. The green part is the window. The current frames allowed to be sent. When we transmit, the window closes on the left side. When we receive an ACK, the window opens on the right side. We're allowed to send another frame, so let's do so. Transmit frame 3. Transmitting frame 3 means that 1, 2 and 3 are now outstanding. We're not allowed to send any more. Okay? We immediately are allowed to send 1 more, so we transmit that frame. So now we cannot send any more, but the ACK for the next frame comes back here. It's about times 610 when it arrives. The ACK arrives back, meaning frame 1 has been acknowledged. Successful, done. Allowed to send 1 more. Transmit 1 more, and now we've got 2, 3 and 0 outstanding. 0 and 1 have been ACKed. 2, 3 and 0 have been transmitted. Not allowed to transmit anymore until we receive the next ACK. The ACK for frame 2. 2 is finished. We can send 1. We transmit 1. 3, 0 and 1 are outstanding. Now we have to wait. If we keep going down. 3, 0 and 1 are outstanding. We're waiting for ACKs. There's no ACKs. We're waiting, we're waiting, we're waiting. Eventually the ACK for frame 3 comes back. Again, 3 is finished. We're allowed to send 1 more. So we transmit that 1 more. And now we have to wait. But then we receive an ACK for frame 0. 0 is finished. And then, although the diagram doesn't show it, we can keep going. We'll receive an ACK for frame 1, allowing us to send the next frame. So what's happening here, if we look at the structure in this example, we send 3 frames and then wait for the ACK for the first frame to come back. You see? 0, 1 and 2, the ACK for frame 0. Then, because the ACKs for 1 and 2 are going to arrive shortly later, we get to transmit another 3 frames, 3, 0 and 1, and then wait for the ACK to come back. And if you keep going, transmit 3 frames, wait for the ACK to come back. 3 frames, wait for the ACK to come back. The window size is 3, or the maximum window size is 3. Sorry, not this one. In this example, maximum window size is 3. So in this specific case, transmit 3 frames, wait for an ACK, another 3 frames, wait for an ACK, and so on. And in terms of the window, if you look at the green boxes, the window says the number of frames we're allowed to send, or the set of frames we're allowed to send. It's initially 3, the maximum size. When we transmit a frame, it closes on the left. That is, it goes from these 3 and it reduces on the left side. As we transmit, the window closes on the left. It's eventually 0. The window means there's no green box here. We cannot send anything. As we receive ACKs, we receive an acknowledgement, it opens on the right. And we receive another ACK, and it opens, and we transmit, it closes. And that's the concept of a sliding window. The green boxes are the window. It slides along as we transmit and data and receive ACKs. It slides along as long as we have data to send. Opening and closing on either side. Yes. How do I know the sequence is 1, 2 or 3? 0, 1, 2, 3. In this case, I told you, or I said, in the header, we have just 2 bits to store the sequence number. You only have 4 values available, 0, 1, 2 and 3. They need to be in order. Sequence number. So whenever, if I have 1,000 packets of data to send, or 1,000 data frames, the first one I'll give sequence number 0, 1, 2, 3, and then the 5th one would be 0, because I need to wrap around because I only have 2 bits to store that value.
So it's 2 to the power of the bit sequence.
It's the, yes, it's 2 to the power of, the number of values is 2 to the power of the number of bits. It's simply, if you have 2 bits, how many decimal numbers can you represent? How do, yep.
Could you explain about
ACK number. Okay, the ACK number is not shown in here or not mentioned here, but when I send a data frame, it has a sequence number. When B responds, it sends an ACK, like this, and they include an ACK number with the idea of saying, for acknowledging a data frame. And the common approach is to say, not what you just received, but to say the next value expected, which is similar. Because if I say the next value expected is 1, that implies that the last one received is 0. Okay? So the ACK includes a number in the header which says the next sequence number expected. Because if I just received 0, the next one should be 1. If I just received 3, the next one should be 0. We'd wrap around. So that's all. It's, you can directly get the last one from it.
But the number is 1, but the data 1 is
Okay, back to our diagram then. So, remember what's happening at A and B differs. So, B at this time is expecting, when it sends an ACK, it's saying it's expecting data frame 1. I've just received data frame 0, I'm expecting data frame 1. And it comes back here. But A knows it has sent frames 0, 1 and 2. So when it receives an ACK saying I'm expecting frame 1, A knows that frame 0 has been successful, but not 1 or 2. But A also knows that it has already sent 1 or 2. It's not going to send again. It just knows that they're going to eventually arrive at B. So we move on to the next one that's allowed. Okay. When we look at error control, we'll see that it becomes more complex. We may lose packets, and that's where the ACK numbers become important as well, or have an impact. Any questions? Any further questions? So the concept is to allow the source to send multiple frames before waiting for an ACK. What this diagram is showing is the concept of the window and what the source keeps track of. In a real implementation, they don't have this, they just have some variables, and those variable values change. We care about the idea of sliding window is we are supposed to improve upon the efficiency compared to stop and wait. That's the idea. Which one's simpler for you, stop and wait or sliding window? If I ask you in the exam, or you get to choose in the exam a question on stop and wait or a question on sliding window, which one would you choose as the simplest, as the easiest? Stop and wait? Stop and wait is simple, okay? And in terms of implementation, sliding window is more complex. It's harder to implement, and we'll see when we talk about buffer, it requires more buffer space. So sliding window is more complex, but it can be more efficient. Let's calculate the efficiency in this example. In this example, I've given you some numbers so we don't have to calculate propagation or transmission time. So we say the propagation is 200, whatever, 200 microseconds, 200 milliseconds of ignored time units. We can say 200 microseconds. That's the propagation delay. The data transmission delay is 100 microseconds, where 90% is real data and 10% is header. So when I transmit my frame, some of it's header, some of it's data. In this example, we're saying that 10% is header and 90% is the payload or real data. ACK transmission time is just 10 microseconds. There's no processing. We've ignored that to keep it simple. 2-bit sequence number, and the blue values indicate the timing in our case. Start transmitting at 0, takes 100 to transmit the data. It takes 200 for that data to propagate, so when we finish transmitting at 100, it arrives at 300 at computer B. 10 to transmit the ACK, and 200 for that ACK to propagate back. Therefore, for the first data frame with sequence number 0, the ACK will arrive at time 510. 100 plus 200 plus 10 plus 200. And we can follow for the other frames as well. And I've given you the numbers. Assume we have an infinite amount of data. This process keeps repeating. We have 3 frames, some waiting time, waiting for the first ACK, then another 3 frames, wait for the ACK, then another 3 frames, wait for an ACK, and you can keep drawing it. It looks like this on a smaller scale. And so on. If we look at what's happening, we get to transmit 3 frames, and then we'll need to wait for the first ACK to come back, and then we'll get to transmit 3 more frames, wait for the first ACK of those 3 to come back, 3, wait, and keep doing that. So we essentially repeat this phase each time. How long is that phase? How long before the first ACK comes back? The answer's on the slide, on the sheet. the first ACK comes back at time 510. That is, this is 510 time units. And again, this would be another 510. And another 510. We see that on our diagram, the first 510 from 0 to 510, and then from 510 up to 1020, which is a difference of 510. And you can keep going. Before we calculate the efficiency, so what we can say is every 510 time units, say microseconds, how many data frames do we send? Every 510 microseconds, how many data frames do we send? How many? Look on your diagram. In the first 510 time units, how many data frames were sent?
3.
What are their sequence numbers?
0, 1, 2.
So from the start, at time 0, we send frame 0, and then frame 1, and then frame 2. At time 510, we receive the ACK for the first frame. And then in the next phase, we transmit 3 frames and then receive an ACK, and so on. Every 510 time units, we're sending 3 frames. And in fact, we're delivering 3 frames to the receiver. Every 510 microseconds, send 3 data frames, and as a result, every 510 microseconds, B receives 3 frames. In that time period of 510 microseconds, how much time do we spend sending real data?
Why is it 510?
Because, why is it 510? Because with the values given, data transmission is 100 plus a propagation of 200. The data arrives at time 300. We transmit an ACK. Transmit an ACK at time 300. It takes 10 to transmit the ACK, and then from 310 to 510 is the propagation time. So it takes 200 to propagate for the ACK. So the ACK for frame 1 arrives at time 510, which allows us to send 1 more frame. And the ACK for frame 2 arrives at 610, which allows us to send frame 0. And the ACK for frame, the third frame arrives at 710, allowing us to send frame 1. But then there's no more ACKs until 10,020. So transmit 3 frames, wait for the ACK for the first frame, and then transmit the next 3. That's what's happening in this scenario. It's not always like this. So what we get on average, we're sending 3 data frames every 510 microseconds. How much real data, or how long do we spend sending real data? Every 510 microseconds. We've got 3 frames. How much time do we spend transmitting real data in 1 frame? 90. Note that the frame has 10 units of header and 90 of real data. So we'd say In that 510 microseconds, we spend 270 microseconds sending real data. That's in here. So we ignore the header, we don't count that, and we don't count the time spent not sending. Efficiency directly comes now. Time spent sending real data over total time equals, and it's at the bottom of your slide, the diagram, about 53%. This one. The efficiency in this case is 53%, or around 53%. What if we didn't use sliding window? What if we used stop and wait? So with our sliding window, it turned out we could send 3 frames and then have to wait for an ACK. An ACK arrives every 510, or that phase lasted for 510 microseconds. 3 frames, where each frame has a transmission time of 100, but 90 of that 100 is real data. The rest is header. So we say the time spent sending real data is 270 microseconds. So every 510 microseconds, I spend 270 sending real data. So that gives me the efficiency. What if I use stop and wait? If I drew stop and wait, it would look like this. And so on. With stop and wait, not sliding window, send one data frame, wait for the ACK to come back, send the next data frame, and so on. What's the efficiency with stop and wait? Well, transmit a data frame takes 100 with the same values as the example. Takes 100 to transmit, 200 to propagate. There's a 10 for the ACK, plus 200 to come back. Total time, still 510. With stop and wait in the same scenario, 510 microseconds, transmit 1 data frame. One data frame every 510. With our sliding window, we got to transmit 3 data frames every 510 microseconds. Every 510 microseconds, we're sending 1 data frame, which takes 90 microseconds of transmitting real data. So we're sending 90 microseconds every 510. It's about 18%. It's 3 times worse than our sliding window case. Because, quite simply, sliding window allowed us to send 3 frames per phase, stop and wait 1 frame per phase. That was the easy part. How can we make it more efficient? Stop and wait, 18%. Sliding window with a window of 3, 53% efficient. I want higher efficiency. What am I going to do to get more efficient? Here's the hint. Stop and wait is sliding window with a window of 1. It's just sliding window. Send one frame, wait. Sliding window, send W frames. Well, stop and wait is sliding window with a window of 1. Our sliding window, we had a window, maximum window of 3. Increasing the window size is increasing our efficiency. Window of 1, we get 18%. Window of 3, 53%. Let's try a window of 7. And that's what the second diagram does. We can send 7 frames before having to wait for an ACK. Follow the diagram. We're always transmitting. Frame 0, 1, 2, 3 are transmitted. 4. We receive the ACK at time 510. We didn't have to stop because we were allowed to send more frames. So we keep transmitting. And if you follow, we would never stop and wait in this case. We'll always transmit frames because the window size is large enough such that we don't have to wait for the first ACK. Or you can see from the diagram, there's always green boxes here. The window is always open. If the window is always open, we never wait for an acknowledgement, and we achieve maximum efficiency. What's the maximum efficiency we can achieve in this example? Can we get 100%?
No.
Why not? The answer's in front of you. The efficiency is the time we spend sending real data. Go back to the top. When we transmit data, we're always sending data, but 10% is header, 90% is real data. So we're always sending data frames. 90% of the time we're sending real data, 10% of the time we're sending header. So we say we're 90% efficient. That's the maximum we can achieve in this case, unless we change the header size. With a window size of 1, that is stop and wait, we got an efficiency of 18%. With a window size of 3, 3 times as efficient, up to 53%. With a window size of 7, we reach the maximum efficiency, 90%. We cannot go any higher because there's always a header. 15, efficiency will be 90%. Window size of 1 million, the efficiency will be 90% because we've always got this 10% of header unless we change the header size. So we can work out what is the optimal window size under particular conditions. In this case, we could calculate, well, in this case, 7 is sufficient. Having a larger window is no better in terms of efficiency. So for today, what you need to understand, you need to be able to calculate performance for stop and wait. That was yesterday. And similar for sliding window. And the concept with sliding window, allow the sender to send multiple frames before waiting for an ACK. To send a window size of frames before waiting for an ACK. Now the window size may vary. And what the sender and the receiver do is they keep track of the frames which they've transmitted and been ACKed, that have been transmitted but not yet ACKed, and those frames which they are allowed to send. And by doing that, they keep changing the window, the current window size. And depending upon the link conditions, like the propagation and data transmission delay, we can achieve maximum efficiency using sliding window if we have a window large enough. In this case, we needed a window of 7 to get it. In fact, a window of 6 would also get it, I think. Any questions on what we've gone through there? We have a bit more to finish next week, but that's enough for today. Let's stop there, we're out of time. What we'll do next week is